We're reaching the end of chapter 4, where we're studying the applications of derivatives. And it's now time to talk about how to undo taking the derivative, or a process called antidifferentiation. When we're doing this is part of the process of mathematics. We learn to add in first grade and subtract in second, multiply in third and divide in fourth. We've learned earlier this semester to take the derivative. Now we want to talk about how to undo the derivative. This process, antidifferentiation, will give us something called the antiderivative. Let's suppose we start with a function lowercase f, and we find another function, the antiderivative of lowercase f, where the antiderivative function is uppercase f, and the derivative of uppercase f gives us the lowercase f function. And we would say that uppercase f is an antiderivative function for the lowercase f. Now, because the derivative of a constant is 0, when we find the antiderivative, we'll actually be finding an entire class of functions, infinitely many different antiderivatives that differ by only a constant. Finding the antiderivative means that we'll always have a plus c. Again, if you had taken the derivative of the function, the constant would have disappeared. So undoing it, you get the antiderivative function up to the constant plus c. Now, why might you want to do this, aside from just this is the math thing to do? Well, let's suppose that you have a position velocity acceleration situation. We know that if I take the derivative of position, I get the velocity function. And the derivative of velocity is acceleration. What if, instead of starting with position, I was given the acceleration function and some information about the velocity function, perhaps the velocity at time equals 0, called the initial velocity. And I'm asked to find the velocity function. Because the acceleration is the derivative of velocity, I have to undo the derivative to get back to velocity. The process of antidifferentiation will give me that value of the antiderivative, the velocity function, up to the constant c. And then I can use my knowledge about the initial velocity to pin down the value of that precise c. Similarly, if I'm given the velocity function and something about the position of the particle at a particular point in time, then I can do the antiderivative of the velocity to get the position function and use that single condition, that known value of position at a point in time, to find the value of the constant. Now, rectilinear motion is just one example of when we would want to undo a derivative, but there are many, many others. Let's take a look now at the learning objectives for this section. In the learning objectives, we're going to start by finding the general antiderivative of a given function. This is the uppercase letter f, the one whose derivative gives us back the lowercase f. This will be good up to a constant plus c. So we'll give the antiderivative function as uppercase f of x plus a constant. We'll explain the terms and the notation that we use for the indefinite integral. That's right, it's time to start integrating. The indefinite integral represents this process of antidifferentiation. When you find the antiderivative, you are doing the indefinite integral. We'll also state the power rule for integrals so that we can integrate some basic functions. And we'll use antidifferentiation, the indefinite integral, to solve some simple initial value problems like the acceleration and velocity problems I used in the introduction. I'm going to share my screen so we can get started. Remember that the antiderivative is the process of undoing the derivative. It's antidifferentiation. Like multiplying and dividing by the same value are opposite directions or inverse operations of each other. Antiderivative undoes the derivative. If we're given a function, lowercase f, and we want to find another function whose derivative gives us that, we're looking for the antiderivative, such that the derivative of uppercase f is the function. Now, we call that the antiderivative function for lowercase f. Let's look at an example. Suppose our function, lowercase f, is the function 2x, which is just a slanted line, slope 2 through the origin. We know the power rule for differentiation. We can imagine and think and come up with a possible antiderivative of x squared. This means that x squared would be an antiderivative of the function 2x because the derivative of x squared is 2x. The question is, are there any other antiderivatives of the function 2x? And the answer is yes, there are in fact infinitely many. Since the derivative of the constant gives you 0, x squared plus any constant real value is also an antiderivative of 2x. So x squared plus 5 and x squared plus the square root of 2, or x squared minus the square root of 2, or x squared plus pi are all antiderivatives of the function 2x. Are there any others that aren't of the form x squared plus a constant? In fact, the answer is no. We know from corollary 2 of the mean value theorem that if two functions have equal derivatives, then they differ by only a constant. F must equal g plus a constant. That means that in this case, x squared plus c is the most general form of writing the antiderivative of 2x. Let's now talk about the theorem for finding the general form. We'll let uppercase f be some antiderivative of the function lowercase f over an interval I. For each constant c, the function uppercase f plus c will also be an antiderivative of the function lowercase f over the interval. Because when we take the derivative of the constant plus c goes to 0. If g is also an antiderivative of the function lowercase f over the interval, there must be some constant where g is equal to uppercase f plus the constant over the interval. Again, our most general form would be given by one of the antiderivatives plus a constant. Let's define a little bit more formally the antiderivative. A function uppercase f is an antiderivative for lowercase f if the derivative of the antiderivative is the function. That's right, we can think of f prime, uppercase f, as the derivative of the antiderivative. As in most operations that undo each other, if you take the antiderivative and then take the derivative of it, you get back to the original, which is our lowercase function f. Let's now look at example 1, where we want to find all the antiderivatives of the function sine x. When we say find all antiderivatives, you obviously can't write them down because you can use any real value for the constant. We mean simply that you find an antiderivative and add a plus c at the end. The most general one is the one where we allow the constant to be 0 and replace it with plus c. I know that if I take the derivative of cosine, I get negative sign, but I want to get positive sign. So what I'm going to do instead is I'm going to find the derivative of negative cosine. I'm looking for a function that when I take the derivative of it, I get the original function. Negative cosine of x is an antiderivative of the function sine x. It's the one with the constant 0. This means the antiderivative function is negative cosine of x plus constant, which gives me an entire family of functions, all vertically shifted from one another. Let's now talk about the indefinite integral. The indefinite integral is, in fact, this antiderivative class of functions. We're going to introduce the notation for integration now. This symbol that you see here is called the integral. The integral looks like an elongated S. If you're looking at it on lined notebook paper, it extends both above and below the line. Make sure that you do not fit the integral inside of a line. Notice that next to it, we have the function that we're trying to find the antiderivative of, lowercase f of x. Next to that, you see the differential. This is the same differential that we saw before, our dx, which is also equal to our delta x. We use the differential dx when we integrate with respect to x. In fact, what the differential is indicating is what the independent variable is for the antiderivative function. When you find an antiderivative function, the variable will always be in there, and you need to know what that independent variable is. Differential tells you. The variable used in the differential will match the variable used for the function we're trying to find the antiderivative of. When we're done, we get the antiderivative function up to a constant plus c. Notice that when you write the notation, the f of x and the differential dx actually fit on the line, which means that they are not even with the bottom of the integral symbol. The integral symbol is longer. It is an elongated S for reasons that we'll discuss when we talk about the Riemann sum coming up in the next video. Let's formally define this indefinite integral. Given a function f, the indefinite integral of the function is denoted with the integral symbol, followed by the function, the differential with the independent variable, and it results in the antiderivative function up to the constant plus c. Let's talk about the different parts of the notation. When we talk about the notation, remember that we have the symbol and we have the function we're trying to find the antiderivative of written in the middle of the symbol, followed by the differential related to the independent variable. When we're looking at this, the function we're trying to take the antiderivative of, in this case f of x, is called the integrand. The differential, of course, is the differential, as it has been since we learned about it at the beginning of chapter 4 in the linear approximation function. Now, this is equal to the antiderivative function up to a constant plus c. When we look at this, we know that the uppercase function f of x is one of the antiderivatives, typically the one where the constant is 0, and the plus c is called the constant of integration. This process of finding the antiderivative function is called integrating the integrand function lowercase f. Now let's talk a little bit more about this family of antiderivatives. Again, the family of antiderivatives is really representing the same graph, but simply peeled off and shifted up or down vertically. In other words, if I'm looking at some of the antiderivatives of the function 2x, x squared plus 2, x squared plus 1, x squared minus 1, and x squared minus 2 are all antiderivatives of 2x. Notice they're exactly the same shape, just shifted up and down. This gives us a family of antiderivatives, infinitely many, one for each real number as the constant. We want to talk about the power rule so that we can, well, evaluate some basic integrals. We'll be spending a lot of time in the rest of this semester and also in calculus 2, learning how to integrate various integrands. When we think about undoing the derivative, let's remind ourselves of what it is that we do when we take the derivative. When we take the derivative with respect to the independent variable of x to the n, we pull the n, the power to the front, and we multiply by the variable to 1 less than the original power. So we need to think about undoing this operation. We know that we reduced the power by 1 was the last thing we did. So the first thing we want to do is increase it back to its original value, which means that the integral of x to the n dx, we add 1 to the power to get back to the original. In the derivative, the first thing we did was pull the original power to the front. To undo that, we divide by the new power, which in fact is, of course, what we had originally. And then we tack on the plus c to get the whole family of antiderivatives. If you check to make sure that this rule works, you can do that by taking the derivative of the antiderivative, which is the indefinite integral. The derivative of x to the n plus 1 over n plus 1 is going to give us the n plus 1 to the front times x to the n divided by the n plus 1, which does not depend on x. The n plus 1's cancel, and you get x to the n. You may wonder why I didn't include the constant, but the derivative of the constant, of course, is 0. Now I want to give you some of the common formulas for the indefinite integral and also their derivative forms. Let's take a look at these now. If I want to undo the derivative on something that is a constant, k, it means that I'm going to have to find a function whose derivative gives me k. I know that one function that does that is the constant times x, and I get kx plus c. In fact, we can think of the constant as a constant times the variable raised to the 0th power, and then we can apply the power rule. Increasing the power by 1 brings it to 1, and dividing by 1 gives us kx. plus c gives us the entire family. This is because the derivative of kx gives us k. We've already discussed the power rule, which you see here in the second row. In the next one, let's think about undoing something related to natural log. If we take the derivative of the natural log of u, we get 1 over u du dx, which must mean that if I'm trying to integrate 1 over x with respect to x, it must give me the natural log of x up to the constant. Now you'll notice that this has an absolute value. That's because natural log will only accept non-negative values, and in fact, they must be strictly positive, not 0 either. We put the absolute value around it, and yes, it is required. What about the derivative of e to a power? It's e to the u du dx. If it's simply e to the x, well, the function whose derivative is e to the x is e to the x. Again, e to the x is one of our favorites to either take the derivative of or integrate because there's not much to do. Let's now look at some of the trig functions. When we look at the trig functions, you can see that we have cosine of x. This does tend to mess students up a little bit because they have to undo the rules that they learned for the derivative. We know that the derivative of sine gives us cosine, so the antiderivative of cosine must be sine, not negative sine. When you undo a derivative on cosine, you get back to sine. On the other hand, since the derivative of cosine is negative sine, the derivative, antiderivative of sine gives us negative cosine up to the constant. Because the derivative of tangent is secant squared, the antiderivative of secant squared gives us the tangent of x up to the constant. And you can see the last two here relate to the derivative of cosecant and the derivative of secant. These are all ones that you probably need to commit to memory. I believe there is one more, which is the integral of cosecant squared of x dx. Because the derivative of cotangent is negative cosecant squared, when you integrate, you get negative cotangent of x back. The last three that you see here are related to the inverse trig functions, the arcsine, arccosine, and arctangent. I do not expect my students to memorize these formulas, but some professors may. Again, notice that when we take the derivative of arcsine, we get a strictly algebraic function. So when we integrate that algebraic function, we get back arcsine. We will learn a better method in Calculus 2 of how to compute these without having to memorize the formula. I will warn you, though, that it's a long process and not simple. So maybe you'd rather commit them to memory. Let's now go ahead and look at examples 2 and 3. In example 2 and 3, we want to show that uppercase f is an antiderivative of lowercase f by showing that the derivative of the antiderivative gets back to the function lowercase f. We want to apply this in both 2 and 3. In other words, if I take the derivative of the result of an indefinite integral, I should get back the integrand, the function inside the indefinite integral. Go ahead and pause the video to work this one out, and turn the video back on so we can discuss. Let's compare our results. To prove that this is the antiderivative of this, I take the derivative of the antiderivative. which gives me 15x squared plus 4x plus 3, which is the lowercase function f. In example 3, it's asking the same question, but in a slightly different format. We have the integral of x times cosine of x dx. In this case, the integrand is x cosine of x, which represents the lowercase function f of x. The antiderivative is x sine x plus cosine x plus the constant. This is the uppercase f of x. To prove that this is true, we want to take the derivative of the antiderivative. Applying the product rule to the first term, we get sine x plus x cosine of x. The derivative of the middle term is minus sine x, and the derivative of the constant gives us 0. Sine x's cancel, and we get x cosine of x, which is the original integrand. This proves that it is the antiderivative function of x cosine x. We want to now look at some of the properties for integrals. Every time we learn a new construct, we have to talk about the properties. So it's time to talk about the properties of the indefinite integral. Let's suppose that we have two antiderivative functions, uppercase letters f and g, of derivatives, lowercase letters f and g, respectively. We'll let k be some constant real number. And the integral of a sum is the sum of the integrals. The integral of a difference is the difference of the integrals. We saw that this rule held for limits, and it also held for derivatives. That means that the indefinite integral of lowercase f of x plus or minus g of x with respect to x dx will give us the indefinite integral of f of x dx plus or minus the indefinite integral of g of x dx, which gives us the sum or difference of the antiderivative functions plus a constant c. The next property has to do with the constant k multiplied by the integrand function in the indefinite integral. If we have the indefinite integral of a constant times the integrand with respect to x, we can take the constant out. Remember that when you take the derivative, if you have a constant, you can factor it out. So it makes sense that in the process of undoing, there's a constant, it can also come out. This gives us the constant times the indefinite integral of f of x dx, which gives us the constant times the antiderivative function. You may wonder why we don't have the constant k times c. The answer is k times c is still a constant. So we roll it together and simply call it plus c again. Now, evaluating integrals that involve products or quotients or compositions is much more complicated. We will learn how to integrate with compositions this semester in a process called U substitution later in chapter 5. However, when we have products and quotients in the integrand function, then we're going to need more advanced techniques, and that will have to wait until Calculus 2. Let's take a look now at example 4. We know that we have the sum and difference rule and the constant rule. So we know we can split this indefinite integral into the sum and difference of 4 indefinite integrals. Go ahead and pause the video, work it out, then turn the video back on so we can compare. Let's look at the result for integrating example 4. I can use the sum and difference rule to break it apart into 4 different indefinite integrals. And I can use the constant rule to pull the factor 4 and 5 and 7 to the front. Notice the last one results in the indefinite integral of simply 1 dx or just dx. I can think of that as 1 times x to the 0th power, since anything except 0 to the 0th power is the number 1. Then I can apply the power rule by adding 1 to the power and dividing by the new power. I apply this to each of the indefinite integrals. Each one carries its own plus c, but I roll them all together into one big plus c, which I tack on the end. Simplifying gives me x to the 4th minus 5/3 x cubed plus 1/2 x squared minus 7x plus c. Make sure when you split up an indefinite integral that you put the differential on every indefinite integral. Think of it as a bookend to the integral symbol. The reason is when we get into calculus 3, we'll no longer have just one independent variable. We may have 2, 3, or more. We need to know what the differential is, so we know which variable we're integrating with respect to. Let's now turn our attention to the next set of exercises. In example 5, we have the exponential e to the x, and we know from the table earlier that the antiderivative is e to the x. Then we have what looks like a polynomial where we can apply the power rule. Last, we have sine of x, but remember we're undoing the derivative, which means we're finding the antiderivative. A function whose derivative is sine is negative cosine. In example 6, we have cosecant cotangent. What function can you think of that when you take the derivative, you get cosecant cotangent? Because it's a cofunction, you know that you may have a negative involved. And then we have a polynomial 3x to which we can apply the power rule. In the last example on this page, we have the square root of x to the 3rd power. When you have radicals, remember to rewrite them as rational exponents. This is the indefinite integral of x to the 3/2 power with respect to x. This means that we can apply the power rule here on the rational exponent. Go ahead and pause the video, then work out these 3 examples and turn the video back on so we can check our results. When I integrate the indefinite integral in example 5, I split it into 3 separate indefinite integrals. Make sure you only split across addition and subtraction. It does not work for multiplication or division. Make sure you only split the integral at a plus or a minus that's out in the open. The integral of e to the x dx gives us e to the x plus a constant, which will roll into the big one. Then I can factor the constant 3 out of the integral of the polynomial. The integral of x squared dx, add 1 to the power to get 3 and divide by the new power, giving me negative 3x cubed over 3, which reduces to negative x cubed. The last indefinite integral is the indefinite integral of sine of x dx. I know that the derivative of negative cosine will give me a positive sign. The antiderivative of sine of x is the function negative cosine of x. I put a big plus c at the end to represent the combination of all constants from any of the indefinite integrals. Let's take a look at example 6. In example 6, I have the indefinite integral of cosecant x cotangent x dx plus 3x. Take the dx out of the middle. Cosecant x cotangent x plus 3x, then dx. I can split this at the addition sign because it's out in the open in the integrand. Now, I cannot split between the cosecant and cotangent because they're multiplied. This gives me the indefinite integral of cosecant cotangent dx plus the indefinite integral of 3x dx. I know that the derivative of negative cosecant would give me a positive cosecant x cotangent x. So its antiderivative is the function negative cosecant. I can factor the 3 constant to the front of the indefinite integral and apply the power rule to the integrand x, obtaining x squared divided by the new power of 2, then multiplied by the constant 3. The result is negative cosecant x plus 3/2 x squared plus a constant. This gives us a family of functions up to the constant whose derivative will give us back the original integrand. Let's now look at example 7, where we have to apply the power rule to a rational exponent. We can rewrite the square root of x cubed as x to the 3/2 power. It is the only term inside of our integrand, so we can apply the power rule immediately. We add 1 to the power 3/2 and divide by that new power. We need a common denominator, so write the 1 as 2/2. 3/2 plus 2/2 is 5/2. Notice that you're dividing by this rational power. When you divide by a fraction, it's the same as multiplying by the reciprocal. I would probably leave the result with a rational exponent, but you can rewrite it as 2/5 times the square root of x raised to the 5th power plus the constant of integration. We have 3 more examples to work in this section. In example number 8, we're integrating the function -1. It is a constant, and remember, we can think of it as -1 times x to the 0 so that we can apply the power rule. In example 9, we have the difference of 2 terms which both have rational exponents. We'll apply the power rule there too. Example 10 is rather trickier, so let's get started, and then I'll let you pause the video and work it out. When we look at example 10, at first, it looks like we cannot evaluate the indefinite integral because we have division. We do have addition, but it's buried inside the numerator of the fraction, so we cannot split the integrand there, because the division is the last thing that's done. However, the denominator is a single term polynomial, which means we can split this apart and think of the integrand instead as 3x squared divided by x squared plus 2 divided by x squared. Because the denominators are the same, we would then add the numerators to get back to the original integrand. However, this now makes the plus sign between them out in the open, and I can reduce each one individually so that I could rewrite this one in the form of the indefinite integral of 3 plus 2x to the -2 with respect to x. Yes, that's right. We'll be able to apply the power rule, provided the power is not a -1. If it's a -1, then that's actually the natural log. Let's go ahead and pause the video. You can work out these 3 examples, then turn the video back on. Let's now look at example 8. Again, when we have a constant for the integrand, we can always think of it as being multiplied by the variable raised to the 0th power. Then we can apply the power rule. Brought the -1 outside the indefinite integral. And then I found the antiderivative function of x to the 0 by adding 1 to the power and dividing by the new power, which is 1. This gives me negative x plus the constant of integration. Looking at example 9, I have the difference of two functions raised to a rational exponent. In this case, I can split the indefinite integral at the subtraction to come up with two indefinite integrals. Make sure that you write the differential on both. I've been known to take off 20% or more for leaving off the differential or the plus c. Then we apply the power rule. Make sure you get a common denominator to combine the fractions. And our result ends up being 3/4 x to the 4/3 minus 3/5 x to the 5/3 plus the constant of integration. Example 10 was the more complicated problem, which we discussed. And we went ahead and began the problem by first dividing each term in the numerator by the monomial denominator. If we had had addition or subtraction in the denominator, this won't work. In that case, you'll have to wait till calculus 2 to find out how we handle those. In this case, we split the numerator by dividing by the monomial denominator to get a rewritten integrand of 3 plus 2 divided by x squared, or 3 plus 2x to the negative 2 power. Then we can split the indefinite integral over each term and pull the constants 3 and 2 to the front. Remember that the integral of 1 dx is the same as x to the 0, which will give me 3x for the antiderivative function. When I apply the power rule to the negative exponent, I can do this for any negative except negative 1. In this case, I add 1 to negative 2 and divide by the new power. Negative 2 plus 1 gives me a negative 1, which gives me the antiderivative negative 2x to the negative 1, or negative 2 divided by x. Why can we not apply the power rule if the exponent is negative 1? If the exponent is negative 1, when you add 1, you get 0. And dividing by the new power will give you division by 0, which is not allowed. When this happens, remember that the integral of 1 over x, or x to the negative 1, is the natural log of the absolute value of x, plus the constant of integration. Now that we've worked a lot of these examples, we want to talk about the situation we talked about at the beginning, where we might, for example, have an acceleration function and know something about the velocity at one point in time, and we want to find the velocity function. In other words, we want to solve what's called an initial value problem. In an initial value problem, you're given a value initially at the beginning. Most of the time, you're given the initial value, which would be the velocity when time is 0. But in fact, you can use the velocity at any point in time to pin down what the constant is. This allows us to find the specific antiderivative function from the entire family of functions that is in fact representing that precise situation. Let's go ahead and talk about what this is in general. This is actually a simple example of what's called a differential equation. A differential equation is when you have the derivative of some function and you're trying to find the antiderivative that solves that particular problem. In other words, if I have dy dx equal to f of x, I'm trying to find a function y whose derivative gives me f of x. This is a part of differential equations, the course that you take as a sophomore or junior, and it's a part of the first semester when you study ordinary differential equations. Let's now look at some of the terminology and then work an example. If we're given a value on the particular function, for example, I don't know what the function y is, but I know that when x is equal to x sub 0, the y value is y sub 0. In other words, I have a point that's on the function I'm trying to find. I know this point, x naught, y naught, is on the antiderivative function. I just don't know what the antiderivative is. This initial value can help me pin down the value of the constant plus c. Now what we're going to do is we're going to take a look at an example. In this example, number 11, we're told that the derivative of some function y with respect to x gives us 3x to the negative 2. We're also given a value that is on the antiderivative function. When x is 1, the y value on that function gives us 2. What we're going to do is undo the derivative. We're going to take the indefinite integral of 3x to the negative 2 to find a general antiderivative, then use our initial value to find the exact c for this situation. There are all kinds of applications for differential equations. Everything from finding the motion of heat through an object, the rate at which water is leaving a tank, even to find the time of death after someone dies. All of these are talking about differential equations. Let's now take a look at example 11 by taking the indefinite integral of 3x to the negative 2 with respect to x. We can take the 3 out of the indefinite integral, but I will tell you now that we often leave it on the inside just knowing that it can be held in abeyance until we're ready to use it. In other words, we don't always rewrite it. Now we apply the power rule, which gives us 3 times x to the negative 2 plus 1 divided by negative 2 plus 1 plus the constant of integration. This is going to give me a negative 3 x to the negative 1 plus a constant. I can also think of this as negative 3 divided by x plus the constant. This is the general class of solutions, but I want the specific solution, which means I'm going to use my initial condition that when x is 1, y is 2. What I found is a function y of x. I'm going to take my value for y when x is 1, and I'm going to set it equal to my antiderivative function with 1 replacing the variable x. In this case, it leads to 2 equals negative 3 plus constant. And if I add the 3 to both sides, I get that my constant of integration must be a positive 5. Because it's a positive 5, I can rewrite my equation, the antiderivative function, as negative 3 divided by x plus 5. This is the specific antiderivative for this situation that passes through the point 1, 2. In this way, if we're given the acceleration function and something about the velocity, we can find the exact velocity function. And if we're given velocity and something about position, we can find the exact position function. Let's use this method to solve the problem in example 12. In example 12, we're told that the derivative of the function f is the cubic function here, and that a point on the antiderivative is the point 0, 0 at the origin. Pause the video and work this out, and then turn the video back on to check your answer. When we look at this problem, Notice that the derivative of the function is given. To find the function, we need to undo the derivative by taking the antiderivative. This is the indefinite integral of this function. When we do that, we can split it into the sum and difference of 4 separate indefinite integrals. You'll notice that I've started pulling the constant out when I rewrote it. In fact, as we move further, you'll find that we often go directly from this step down to this step, skipping the intermediate steps as we do them in our head. When you're learning, it's a good idea to write it down to avoid careless mistakes and to really get the rules solidified in your brain. We are going to apply the power rule to each of these indefinite integrals, remembering that the integral of a constant dx is the same as the integral of the constant times x to the 0 dx. When we apply the power rule and simplify, we get 1/4 x to the 4th minus 8/3 x cubed plus 8x squared plus x up to the constant of integration. To find the exact antiderivative function that passes through the origin, we substitute into this function the x value of 0 and set it equal to the y value of 0. I went ahead and wrote it all out, but of course you know that every term with x in it is going to 0 out, which gives us that the constant is in fact 0. This means that the antiderivative function is given by x to the 4th divided by 4 minus 8/3 x cubed plus 8x squared plus x. This is the end of our study of the applications of the derivative. This ends chapter 4. We've been introduced initially to the indefinite integral. In the next chapter, we'll also learn about the definite integral. In the first section, in the next video, we'll be studying what are called Riemann sums, which is a way of approximating the area between a curve and the independent axis. I hope you'll join me for that next video.